And now we have used the time for introducing Saul Perlmutter to have questions instead, and I think that's a much better use of the time, because a Nobel Prize winner doesn't have to be introduced. That's a well-known person. So I'm happy to give the floor now to Saul Perlmutter. Give his presentation.
Until what time should I aim for?
Until, let's see, 12 or 10.
Okay, good. So can you hear me? Does that sound good? Good, thank you. Good morning. It's a pleasure to be here. I thought that the idea that Brian and I had would be that I would now pick up with the story in a way where you got a little bit of a sense for the texture of what the issues were that we all faced when we were actually trying to do this work. And I hope that I'll give you a little bit of a feel for how this kind of project occurs. And I also decided to use the original, mostly the original graphics, the original plots from the overhead transparencies that we were using during that period. So it won't be the slickest graphics, but it's for historical reasons, so you get a sense for what we were looking at, during these periods. And then if there's a little bit of time at the end, I may try and give you a sense of what the experience felt like from a human point of view, what kinds of things were going on in these research groups at the time as well. I want to just begin with the comment that these sorts of projects that we're talking about here, I think are really getting at questions that are very fundamental to humans. I could always imagine the first human walking outside of their cave at night and look up at the stars and find themselves wondering, does it go on forever in space and will it last forever in time? And I've been commenting that I sometimes think that may be almost what defines what it meant to be the first human, that you would find yourself asking that kind of question. And what's interesting is that these kinds of questions turn from being questions that you could ask a philosopher in this past century to questions that you could ask a scientist who's doing measurements. And I think from Brian's talk, you probably by now have understood the idea that you can guess what the fate of the universe would be, what it will do in the future, whether it will expand forever or turn over and then collapse, based on what happened in the past, by looking back to what it was doing going back in time. And this is something, of course, that the supernova are providing us a very direct measurement of. And in fact, one of the surprisingly simple measurements that I know of that gets at something so fundamental. In this case, you're using the relative brightness of the supernova. The ones that are brighter are nearer, the ones that are fainter are farther away. And of course, the farther they are, the farther back in time you're looking, because it takes time for light to travel to us from a further distance. So the brightness is basically telling you how far back in time you're looking. And then the color of the supernova, where the lines are in the spectra, is a very direct measurement of the expansion history of the relative scale of the universe, how much the universe has stretched since that explosion time. And so the supernova sends its photons mostly in the blue. By the time they reach us, they look red, and how red they look is a direct stretching. That's exactly the measurement of how much the universe has stretched since that explosion. And so you can plot each supernova one at a time, and its brightness versus its redshift tells you the relative size of the universe, the average distance between galaxies, as a function of how far back in time you're looking. And we just want to go back to this distance to be able to see what was going on. So we knew this for actually many, many decades. This is actually something that had been proposed by Baade and Zwicky back in the 30s, just a few years after Hubble was discussing the expansion of the universe. So why couldn't we have done this all along? Well, of course, the problem was that the standard candles that we had available to us at that point didn't seem good enough. The supernova were a little bit too broad a distribution, well, actually a lot too broad a distribution of brightnesses at their peak brightness. And really what got us going in this field was in the 1980s, there was two new developments that I think really got us to start working on this. The first development was the idea that you could subdivide the Type 1a supernova into subclassifications, and it became recognized that there was a group that we were calling the Type 1a supernova. That's a subcategory among the Type 1 supernova. And this had to do with whether or not you had hydrogen in the atmosphere, and that told you that it wasn't a Type 2, and whether or not helium, it was telling you whether it's Type 1a. So it was that kind of classification. And there were a series of papers that were very influential that came out just around the middle of the 1980s that pointed out that these type 1As looked like a subgroup that we should be studying. And in particular, there was a recognition that they seem to be a tighter distribution than the broad spectrum of supernova. In this case, Nino Panagia's paper was pointing out that the supernova found in elliptical host of galaxies, which turn out to all be type 1As, were more tightly distributed. And this actually was one of the things that made us realize, it's time to go back and revisit this, this idea from the 1930s to use supernova to make this measurement. There was another new development, though, which was that the CCD detectors, that we all have now in the back of our cameras and our cell phones to take pictures with, that they were just being developed. In fact, we were doing one of the experiments, one project, so I'll tell you about using the one of the first generation that had 320 by 512 pixels. And if you think about your modern day cell phone, you smile. But that was a major step forward for astronomy because you now had the capability of a much more sensitive measurement. These were much more sensitive than the photographic plates that were being used previously for imaging. And yet also you could read it into a computer. And that was the other technological development, that the computers were now getting fast enough that you could analyze these images that you're reading out of the CCDs. And I will say you could just barely analyze them at that time. They were not very speedy computers either compared to your cell phone today. So, but nonetheless, that was, those two things made us realize that it was time to revisit this question. And in particular, there was a suggestion by the Nobel laureate, Luis Alvarez, who was my research advisor's research advisor. So my research advisor was Rich Mower. His research advisor was Luis Alvarez, so I'm the grand student of Luis Alvarez. And he was still working in the group when I joined the group, as a matter of fact, so we worked together. He suggested to Rich Mower that it was time to try to go back to do a project, a robotic supernova search, which had been first proposed by Sterling Colgate. And he tried to do it, but the technology just wasn't up to the job, and he had just about given up at about that time that we began this project. But now it seemed possible to do, and Rich Mower started this Berkeley-made supernova search. I was a young student in the group. I was working with Carl Pennypacker, who was a young postdoc in the group. And it ended up being very successful. We found that with the technology of the time, we were able to subtract images of, let's say, a supernova plus a galaxy, and you take off the galaxy and you're left with just the supernova. And this was one of the examples of a supernova we found. The project found some 20 supernova in this automated fashion. This was a major breakthrough in some sense, but it was also just catching up to the humans in another sense. There was a amateur astronomer who was at that point the most productive supernova discoverer. He would go out in his backyard every night and do the same thing by eye. He would just recognize what some 300 galaxies looked like in the sky, and he could tell when there was a new spot of light. So we were just catching up, but nonetheless, it was a big step forward, and it also meant that we had this moment where Carl came into my office and we started talking about the idea that these type 1A supernova looked like we could actually go much further out. They're very bright, and that maybe we could do the project at much further distances. These were just nearby supernova that we were finding. And if we go back far enough, we could actually do that Bader-Zwicky idea of measuring the deceleration, we thought, of the universe, how much the universe was slowing down. And we knew it was going to be very difficult. We recognized already that there was a series of problems that we would have to address if we were going to make this work. And what I'll tell you about then in this talk is basically what each of them looked like and what these solutions turned out to be for these different problems. And these were problems of could you find the things, could you identify them, were they going to be standard enough, would they not change over time? And let me begin with the first of these, which is, can you find these at distances that are appreciable so that you can do the cosmological measurements? Can you look far enough back in time? And can you find them early enough so that you can catch them before they reach their peak brightness, which is where you calibrate them all being the same brightness? And at the time, this wasn't obvious. When I've said to you type 1As are wonderful to do this measurement, I speak loosely because really, if you have any option at all to use anything else to do your research, I would recommend it. They're a real pain in the neck to work with. These things are first of all, they're really rare. They only are exploding a couple of times per millennium in a given galaxy, and there's only so long you want to do your research. They're random. They give you no advance warning when they're going to explode, so you can't propose to use a telescope 6 months from now on a certain night. And then they disappear before you get a chance to get back with the telescope. They only rise in a few weeks, and they fade in a month or two. And it's a terrible research tool. So we have to figure out a way to start to use them in more systematically. The first part of the problem was handling the fact that they're very rare in a given galaxy. Now, of course, the way to get around that is to look at a lot of galaxies. And I should say that this is something that just around the time that we were beginning the project, we learned about another project that had been trying to do this by looking at clusters of galaxies, where you would have a fair number of galaxies together. And this was encouraging in one sense because they were able to find a supernova at cosmological distance, this redshift of 0.31. And so we knew that they existed. At least one existed out there. But the problem was that after several years of intensive searching, they'd still only found one. And that one was found several weeks after it had peaked. And so in that sense, it was a little bit worrying that how were we going to make this thing work? What we ended up doing was developing a new wide field camera that we mounted on the AAT 4-meter telescope, where with this unusual optics, we were able to bring a slightly larger field of view down to a small CCD chip. This one was a really big chip. It was 1,000 by 1,000 pixels. You're once more dwarfed by anything you own today. And that means that now you're able to look at hundreds of galaxies at a time, not just a few, and in fact 10 to 20 times more than the Danish group was looking at in a cluster of galaxies. And so now there was a reasonable odds that on a given night, if you looked at thousands of galaxies over the course of the whole night, you could pretty much guarantee there'd be some supernova there. And so that was the beginning of the idea here. The images looked like this. You were looking in these little faint smudges here, not these big bright things, but the little faint ones. These are all the distant galaxies in which you're trying to find a supernova. And then you would subtract off another image taken from a few weeks earlier, sort of line them up, and then look for the spots that show up that are different. Now, of course, we were doing this not with transparencies, but we were developing a lot of computer software. And of course, as you heard from Brian, that was almost all the work in many of the early years was developing the software to make this work and letting the computer find that spot that was the new supernova light. And the techniques basically got up and running, and they worked. We were finding things that looked like supernova, but we weren't able to confirm that they were a type 1a supernova because there's a chicken and egg problem for telescope time. You have to apply months in advance to use a telescope, and it made a pretty crummy proposal to say, we'd like the night of March the 3rd because we may or may not find a supernova on March the 3rd. Maybe we'll have found it in January or perhaps in April, but March the 3rd is when we'd like. It didn't work, and of course by the time, because they're random, you didn't know when you were going to find them, and you also you would have a hard time because they'd have disappeared very quickly, so you couldn't apply for the next semester for telescope time. So one of the things that was important at this point is that we realized that we came up with a way of organizing the time where we would. Oh, and I should comment that there were other very systematic searches going on at this time for nearby supernova. For example, the Clance Lolo search, which I will tell you about, and Brian mentioned, was systematically coming back over and over again with photographic plates. But even so, they were in this funny position where the appearance of the supernova is not predictable, and this is from a paper that they wrote several years into the project. So you cannot schedule the follow-up observations, and you usually have to rely on someone else's telescope time, making the execution of the project somewhat difficult. Now, somewhat difficult at low redshift, where the supernovae are pretty bright and you only need to borrow a little bit of time on a small telescope, is one thing. Trying to get somebody to let you use the largest telescopes in the world for an appreciable amount of time, just on your phone call, is, well, I'm sometimes pretty persuasive on the telephone, but we weren't going to be able to do this very long. And so it was clear we needed some more systematic way of being able to handle this. So the idea was that you want to observe all of your observations clumped together. That was the solution to this problem. You put all of your observations into just a few nights after a new moon, and then you time it so you get the next set of observations for the repeats of the same fields just a few nights before the next new moon. Now, when you find new supernova in the second night here, they are on their way up because there isn't enough time in those just 2.5 weeks for the supernova to make their way to their peak. And Furthermore, you found them just before new moon, so they're going to peak and start fading right over the dark time of the month, which is the time of the month that you need to observe these distant supernovae with spectroscopy. And for that matter, you can now start to schedule spectroscopy and the follow-up photometry to get the data points as it brightened and faded away. And this approach turned out to work. And I remember the first time one of the first times we were using it, we called up the International Astronomical Union telegram service ahead of time to warn them that we were about to find a series of supernovae. These are the telegrams that were sent out, and they were sent out as circulars to all the observers around the world, warning them of unusual new transient events that they may want to study. And they were very careful about who they allowed to announce a supernova and what counted as a supernova discovery, so they wouldn't have false alarms. And so I thought we'd better discuss it ahead of time, so we knew what criterion we were going to be trying to meet. And of course, they laughed because I was predicting the discovery of a batch of supernova. Now, nobody had predicted on a day on which they were going to find a supernova before, and nobody had ever, I don't think there had been very many supernovae found more than one at a time previously. And here I was saying, on this date, November, whatever, we're going to have a half dozen, and they laughed. But sure enough, we started getting telegrams like this out every semester. With, in this case, I think that one turned out to be more than half a dozen that time. And it became sort of a standard way of doing business. Every semester, you would go out and you would do these runs, and you would find another half dozen to a dozen supernova. And now it was a research project. You actually could propose for time and be working and doing all the follow-up observations. We were proposing now for telescopes around the world to do these follow-ups, and things moved ahead. This was the solution to the first problem. The second problem, of course, was once you found the things, are you going to be able to recognize this as a type 1a supernova? These are very faint objects that you're going to be observing, and you may not be able to get enough signal to be able to see it in the noise. Furthermore, now their brightness is going to be difficult to compare distant to nearby ones because the spectrum gets shifted to the red, as I mentioned, because of the stretch of the universe. So, sure enough, the data looks like noise when you first see it. It's just this forest of lines here, and it took us a little bit of thinking before we realized that we don't care actually about these very narrow lines that you often study in astronomy. For supernova, they're all broadened. It's very the wavelengths are all spread out because it's an expanding atmosphere, an explosion. And so you get the Doppler shifts from all different parts of the atmosphere. And almost nothing that's narrow matters for recognizing a supernova. You care about the broad wiggles. So now you can cut out the sharp lines, you can smooth the rest, and now you can compare the smoothed spectrum to a nearby, I'm losing this here, let's try that, to a nearby example of a supernova that's been redshifted, and you keep it sliding over until it matches at the correct redshift, and that now is an excellent identification. Much louder. Am I okay? That's a much better, a fine way of identifying a type 1a supernova, and it gives you the redshift, and so we had a way to go there. Now, of course, with that redshifted spectrum, you're going to now try to compare something at high redshift to low redshift, and you realize that there's another problem, which is that the measurement of how bright it is done through a filter. In this case, for example, a blue filter is used where most of the light is for the supernova. This is the spectrum of the supernova, and this is the blue filter you see it through. And so you make a measurement at low redshift of that supernova light, but now you want to compare it to the high redshift supernova. It's all been redshifted over here, so that same filter is only seeing a tiny tail of the spectrum distribution of where the energy is. And so you have to do what's called a K correction traditionally in astronomy, where you know what the spectrum shape is, and you say, all right, I'm going to see something much fainter here than I would if I was measuring over a peak. But it's partly fainter not because of the distance, but just because it's this part of the spectrum instead of this part of the spectrum. And the problem is that the paper, for example, that was published by Bruno Liebenglit in 1990, actually trying to estimate how big that correction would have to be, the supernova spectrum were not that well known, and so the error bars were huge. And the uncertainty in that particular correction was larger than anything you could use for the cosmological measurements. It was just going to be a useless measurement if that was what you had to deal with. When we found our first supernova at high redshift, it was at redshift 0.458, so this is around this one here, and we realized that there's actually a better way of doing this particular part of the analysis. And that was to, instead of observing the supernova in the blue filter, use a red filter, the R filter. And there, you actually are seeing almost the same parts of the spectrum coming through the R filter at high redshift as you see coming through the blue filter at low redshift. And so now the K correction, it becomes a much smaller difference between what you're doing there and what you're doing here. And we had a route to proceed. We called this the cross-filter K correction. And there had been some use of something like this similarly for galaxies in the past, but it was particularly important for the supernova work. And so that really became the tool that I think we all used to make this kind of measurement from then on. All right, we'd solved item 2, but now what about item 3? How are the supernova in fact standard enough? And can we handle the fact that dust could be dimming the supernova? You could have some absorption in the line of sight between you and the supernova. Now, this paper by Panji I mentioned was showing this, standard candle nature of the supernova. There were other papers at the time. There's a particularly influential series of papers by Bruno Leibengut and Gustav Taman, then in Switzerland at that period, where they were showing these beautiful catalogs of type 1a supernova and showing how closely they matched each other in many cases. And so that was actually very promising. To me, another very influential part of the story was the work of David Branch's group in Oklahoma. And they published a series of papers analyzing the nearby supernova data. This is a plot at that time that we'd made from one of the slightly later papers, where they were showing that if you compare the brightness of the supernova against the redshift, if it's a standard candle, it'll be on a straight line. And as you can see, many of these supernovae are right along the straight line, but there are these outliers here that, in principle, could just ruin the entire measurement. And what that group pointed out, David Branch's group, was that you could handle this in a rather simple way, which was just to identify the ones that are red, and it turns out that these guys are all the reddest supernovae, and just throw them out. And if you threw out those supernovae, you'd be eliminating those which we believed were being absorbed by dust, which tends to redden the light as it comes through the dust. And you'll also be throwing out some of the oddball type 1a supernova, the ones that aren't exploding in the same way as the others, apparently. And by just doing that, you're left with this amazingly sharp distribution. At the time, that scatter, when they first plotted it, went down from an observed distribution dispersion near the peak magnitude of around 40 to 50% to something like 30% when you cut out the red ones. And this 30% was an observed dispersion, and it included all the measurement error. And so the measurements were not that great. So it left the possibility that the type 1a supernova were even a better standard candle and perhaps even perfect. And so it made a huge difference when there were better measurements made. So there was a beautiful data set that came out of the Calan-Tololo Supernova Research. This was Mario Amui, Jose Maza, Mark Phillips, Nick Sunsef and collaborators were doing this photographic plate survey that I was describing and then following up the data with very careful measurements. And this was the first, I think, high-precision data set of supernova that was available from the low redshift set. And with this beautiful set that they prepared, now using the same basic just selection where you cut one color, the dispersion went down from 30% down to some 18%. That's and that's 18% in brightness, which is 9% in distance. So this was actually now going to be a pretty good standard candle. This is really useful for the cosmological measurements. So we felt that now that we had an approach that would do the job, things got even a little bit better in the next year or so, in fact, because we could have done it just with that, I think, but it was even better when Mark Phillips then pointed out that you could use the speed with which the supernova decline, how fast they fade, to predict the variation in brightnesses of the type 1a supernova so that you could make an even better candle, a calibrated candle. There's some beautiful statistical work by by Adam Rees and Bill Press and Bob Kirshner. And then we ended up using a third approach to measure the same thing, which was the stretch of the time scale of the supernova. And if you just measured, took a template and stretched it or contracted it to match whatever that particular supernova looked like, that stretch factor predicted the brightness of the supernova, and you could bring them all into alignment with each other in this calibration technique, which was surprisingly good at that time. All right, so we had this part of the problem handled, but there were other approaches besides just throwing out the red supernova that you could consider for the dust. One of them was to correct each supernova individually for how red it was. And at the time, I felt that the data from all the groups, I felt wasn't quite good enough to do this in a way that didn't introduce some biases into the story. So we also proposed another idea of just comparing the color distribution of high redshift and low redshift. And that gave you some confidence that you were not seeing a different population of dust out there than you were here. It didn't matter, in fact, if the dust out there, if there was some dust out there and there was some dust closer in, as long as it was a matched set. And so that also was a helpful approach at the time. And so then we moved on to the question of, couldn't the supernova evolve over the 5 billion years back in time that we're looking? How do we know that they're the same brightness then as they are now? And here we had proposed an idea, this is from a later paper where we used it again, of looking at the supernova in different host environments. So there was supernova in elliptical galaxies, there was supernova in these early spirals, there was supernova in the late spirals. If you did the project separately for the supernova just in early spirals, comparing nearby supernova in early spirals, nearby supernova in early spirals to distant supernovas in early spirals, then compare that cosmology measurement to the measurements you get from just supernova found in ellipticals, say. And if you get the same result, that gives you some confidence that evolution isn't really what's affecting the result badly, because those environments evolve quite differently. And so that was we felt a good test, and so that was one of the approaches that we proposed at that time. We had all these problems then in hand when we realized in the early 90s that there was an additional problem that is of a slightly different character. This is a problem of the fact that we were now beginning to worry that Einstein's cosmological constant was starting to become of interest again in the field. And this was a worry because it would act to fight against the gravity attraction that would slow the expansion. And this, as you've heard, this cosmological constant would tend to speed up the expansion. So how do you know when you make a certain measurement which you're seeing? It's very easy for the two to get to, it could be that you're seeing something with more mass or something with less, or less mass or more cosmological constant, and you wouldn't know which was in play. Ariel Gubar from Stockholm at that time was visiting us as a young postdoc, and he and I started bouncing these ideas around together, and we realized that there was a way out of this problem, this degeneracy. And that was, if you made a single measurement of a supernova, in fact, you did have this problem. This was, hypothetically, we hadn't yet found one at redshift 0.5, but if we imagine if you had one at 0.5, its magnitude told you that you were along this strip with the error bar telling you how wide that strip is. And so you could have more mass density and more cosmological constant, or you could have less of each. You didn't know. You were anywhere along this strip, and that was a problem. However, because the effects are different at different redshifts, you could go to a higher redshift, and we hypothetically imagined that we could find them at redshifts as high as 1. Now, at that point, that was a real big stretch, but we thought it was possible to do. And we estimated how much time it would take on a big telescope to do it. And now the strip starts to rotate, and if you had some supernova at one redshift, some another, you could look for the intersection and begin to tell how much of cosmological constant and how much of mass density you had. And in fact, if you had a whole series of supernova, you could tell them apart. And so this really got us going on this next step of the project. And we started now being in the stage where we were running that search over and over again, semester after semester, using telescopes around the world and beginning the Hubble Space Telescope. And now we're building up these histograms of the redshifts that we're finding. So first semester we found supernova mostly at this redshift. And then the next semester the green ones came in, here the orange ones, here the yellow ones. And so you start building up a population of supernova, and we were starting to become ready to ask the question, what is the cosmological result that we get out of all this? I should mention that one that was very exciting was we actually did get one way up here above redshift of 1 at redshift 1.2 by doing a special search with the Keck telescope, and we were able to demonstrate that it's possible to study the supernova out in the time when the universe really was decelerating, and that's I think kicked off this work at a very, very high redshift, and you heard the conclusion that Adam Rees had found that we saw that the deceleration did turn back over again, and so we knew it wasn't these odd forms of gray dust. All right, the first data set that we analyzed, the first few, tended to point to a more high-density universe, which, of course, made many people very comfortable, because that's what they were hoping we would see. But you see the errors were fairly big at that time, and this down here, this redshift. As soon as we added the first higher redshift supernova, this was the Hubble Space Telescope measurement, and so it actually had more precision, suddenly the favored line now moves up here, and you're starting to look at something that looks like it's either, well, it's certainly low mass, but it's even low enough mass that you begin to start wondering about a cosmological constant. But of course, you don't wonder for very long, because now you have 42 supernova, which for those who've heard the Hitchhiker's Guide to the Galaxy seems like a auspicious number. With the 42 supernova now, you find yourself looking at this cloud of supernova that are really favoring this really surprising result that you heard about of a universe that's accelerating. And now we have to face this plot that we thought we were going to find one of these lines as the answer, and we put the data on the plot, and we missed all those lines, and we are apparently living in a universe that was decelerating and is now accelerating. And of course, that's why we believe we now have this odd situation where most of the universe is something we've never explored before, this dark energy. Or, even worse, we have to modify Einstein's theory of general relativity, which would be incredible if true. So the theorists, of course, went to town. And I've been estimating that there's been a paper every day since the discovery, on average, from the theorists, trying out ideas. And if you ask the theorists, they'll cheerfully admit to you that they don't stand behind their theory as the answer. They say that they're just broadening the range of possibilities. And that really, what one thing they're doing is they're coming up with these great names for their theories. I love big rip cosmology, the ekpyrotic universe I can barely pronounce. So they're wonderful names, but they really are saying the ball is back in our court, and they're turning back to us, the observers, the experimentalists, and saying we've got to help narrow in on some of the properties of this unusual stuff, so that it gives them a chance to say, oh, okay, if it's in this part of phase space, then now I have an idea of what's going on, and so really the ball is back in our court. Now, it's not true that we've just been sitting around, waiting in the last 10, 12 years. It's been a very productive, very busy period in the field. And first, on the supernova side, those plots that I showed you earlier with some, 50 supernova between the two teams, if you turn it over and flip it upside down and rotate it around to show you what a usual astronomer plot looks like, it's now very different from 50 supernova. It's now over 500 supernova. And each of these, almost every one of these 500 supernova is better measured than almost any of those supernova from those first 50. So there's been a lot of work, and this data set, with many different projects, and the data sets are looking, are now starting to look very beautiful. But I'm now going to just step way ahead and show you, the consequence of this today is that when you make these estimates of what the dark energy density is versus the mass density, we're now we have this relatively tight contour for where the supernova is narrowing in on, and we also have other techniques in play that we can then compare it to. For example, I'll talk about this in a second. The baryon acoustic oscillation and the CMB are coming in from other angles, and everybody's sort of coming in on a nice measurement here that's giving you some confidence that you know how much stuff there is in the universe. This all sounds great, but then when you start to measure the properties of the stuff, for example, that Brian mentioned the equation of state ratio, pressure over density, W, you now actually still have a fairly big error bar, and most of the theories would lie within this error bar, even when you combine these different techniques together for the baryon acoustic oscillation and CMB and with the supernova. But worse than that, these kinds of plots are only if you're assuming that there's a constant equation of state, and we've no reason to be sure of that. As far as we know, the equation of state could change. And so when you start to see, well, how good are our measurements for this equation of state, this dark energy springiness as a function of redshift, you can see the error bars become huge. There's almost no constraints as you get out much beyond redshift of 0.5. This is Already this is so big that it includes almost all theories that you could imagine, including things that aren't even much of a dark energy at all. So we have a big job in front of us because we have to take the supernova project, the supernova technique, and make it even more accurate than we've done today. We think we know how to do this. And so there are a number of projects that are now being proposed where we could make a measurement, a level of detail that would allow us to go from the low redshift all the way out to these higher redshifts with essentially we'd be getting a 20 times improvement of error bar over the original measurements that I showed you with the discovery was seen with. But it's not just supernova that are in play. In the past 10 years, we've developed several other techniques as a community, as in the cosmology field. And I'll just say a word or two about a couple of them. Where the supernova measure using low redshift supernova as a standard candle and as a standard to compare against as you go to higher redshift, there's another approach to measuring things using the distance between the hot and cold spots on that glow left over from the Big Bang, the CMB, as a measuring stick, and then going forward in time to asking where did the galaxies end up and the overdensities of galaxies from the overdensities that are represented by the hot and cold spots in the original cosmic microwave background. So that's your ruler, and then you see how that ruler is stretched as you get to where the galaxies are today. That's what the baryon acoustic oscillation technique is doing. And so that technique is coming along very well. There's some new projects that have been proposed that would allow us to take this all the way up to overlap the supernova data, forward in time. And then there's an orthogonal approach that's been, where a lot of work's gone into what's called gravitational weak lensing, where you measure the distortion of the shapes of these distant galaxies, and they're distorted by where the light is traveling to us around and being gravitationally bent around the intervening mass between us and the distant galaxies. So this technique is very sensitive to the clumping of mass in the universe, and the clumping is slowed, well, it doesn't clump as easily when the universe is expanding faster, so it's sensitive to the expansion of the history of the universe. But also, if there are changes to Einstein's theory of general relativity, you might expect that it'll show up in these very large-scale clumping behavior that the weak lensing is sensitive to. So by having techniques like weak lensing plus supernova plus baryon oscillations all used at the same time, we think we can begin to tease apart the explanations for what could be causing the acceleration, those that would tend to affect the expansion history versus those that would be a change in Einstein's theory of general relativity that could affect the gravitation. So I'm not going to say much more about this except to comment that I think are at a very interesting stage in our progress, that there are a number of proposed projects that are now going through all the committees and are going through strong and strong recommendations to go ahead. The European space satellite that would do the weak lensing and some supernova and the baryon acoustic oscillation work was just recently approved, in fact the same day as Nobel Prize announcement, and so we think it's going to go ahead. The U.S. version, WFIRST, has gone through its committees and been approved 3 times now, and been funded 3 times now. So I'm a little bit worried about this because, if you say it was approved and funded once, that's good news. If you say it had to then be reapproved and then funded again, and then reapproved and funded again, it's been now 8 years worth of these approvals. So I think that the Europeans might actually get there first on this, despite the name. And then there's some ground-based techniques, LSST, for a very full field view of the gravitational weak lensing. Big Boss would be able to do the baryon acoustic oscillation from the ground. And I think that these have very strong chances of actually going ahead. And so I'm rather optimistic that if you invite, well, I hope it'll be other teams that you'll get to invite back in 10 years, and there may be another Nobel lecture in which we get to hear the answer to why is it that the universe is accelerating. It's a tough problem. We have no guarantee that we'll get to know it that in our own lifetimes. But on the other hand, the cosmology field has been moving forward at a tremendous rate. We've learned so much in a relatively short time that I think while we're still getting new data that we've never seen before, I think we have the possibility that we're going to get new answers that we haven't known before. So that's where I want to leave the science story. But if you want to bear with me for just a few more minutes, I wanted to so step back on the human side, because what does it feel like to do this kind of science? And I've described it, I think, today so far as if it's a very cut and dried a process where you see what a problem is, you solve the problem. You see a problem, you solve the problem, and then you go out and you make your measurement, you get your answer, and you're done. And it doesn't feel like that at all. It's a whirlwind of people and activities, and so unfortunately, I wish I'd had photographs of us doing all this stuff, but you realize later that while you're doing it, you have no time to get your camera out, and so there's almost no record of showing us in action, what it really looked like. So instead, I've come up with sort of a bit of a verbal portrait of what it felt like, and if you'll bear with me, I'll read it to you, because I wrote it down so that even at my rapid fire speed of speech, I might be able to capture it a little more accurately if I read what I had. So if you'll, I'll give you a sense that it all begins with a sort of brainstorming in Berkeley with Carl Pennypacker in 1987 as we first batted around hardware and software plans for a new high redshift supernova project in Rich Muller's group, which Rich soon embraced. And then the consequence, the Mountaintop Observatory Cafeteria at Coonabarabran, as Carl, graduate student Heidi Newberg, and former grad student Shane Burns got to know our pioneering Australia-based colleagues, Warwick Couch and Brian Boyle, installing and then using our weird crystal ball of a wide-field corrector and camera at the AET 4-meter telescope, which led to our first high redshift but unconfirmed supernova. And then back in Berkeley, I have an image of Gerson Goldhaber, who is overlaying transparencies with negative and positive images of fields full of galaxies, and this is image analysis for the days when the computer's down. And I was pausing here at the Nobel lecture, and I want to do it again here just to say that Gerson Goldhaber, a number of you know because he also had many Swedish colleagues, and particularly in his particle physics days. And we're really sad that he's not here with us today. He just died just a little over a year ago, and he was this, the heart of our group and the sharp eyes of our group. And we had all the celebration parties at his house, and he would have loved to have been here. And I just wanted to say that because it's sad to not have one of the key members. All right, so back in Australia, we had rain, and then more clouds, and then the sunny relief of beautiful La Palma, where our new Cambridge colleagues, Richard McMahon, working with Mike Irwin, studied the most distant quasars. Long nights debugging a new instrument for La Palma, and tense phone calls to the Isaac Newton telescope while the data was sent to Berkeley for analysis. And then our first official high redshift supernova, a crucial La Palma spectrum from the Herschel telescope as Richard Ellis by now has joined the team after being one of the Danish group pioneers. And then finally, by this point, the Europeans had arrived full force in Berkeley. And so Ariel Gubar from Stockholm kicked the whole thing off, developing new analyses with our then graduate student Alex Kim, brainstorming with me about the cosmological measurements. And then we have a glimpse of Renaud Pin from Paris assessing the damage and successes at the end of a complex telescope run, the first of the so-called batch discoveries. This epic ends, in my mind, with a celebratory party at Gerson Goldhaber's in the Berkeley Hills, where we had bottles of champagne for each of the half-dozen supernova discovered in that first batch. And then the sociology changes just a little bit as we move to mass production with new outposts at telescopes around the world, typically manned by a lone team member tenuously connected by a stream of email, phone, and fax. So Pilar Ruiz Lapuente and Nick Walton were at La Palma, Chris Lidman is the voice at VLT in Chile, Brad Schaefer at Kitt Peak. Larger expeditionary forces head to Cerro Tololo in Chile, where all the supernova discoveries are now generated, and I picture Don Groom and Susanna Destuel on one such trip. Immediately followed by another team of us rushing with a new list of likely supernova to the oxygen-poor mountaintop of the then new Keck telescope. And I have a memory video clip of Alex Filippenko and his student Tom Matheson. And Alex was then on our team. And our new Cambridge PhD, Isabel Hook, and we were all crowding around the computer screen as supernova after supernova proved itself. And the first time that happened, it was amazing to see. And at the control center at Berkeley, the graduate students working around the clock, and I picture Matthew Kim and from France, Sebastien Fabreau, in the cramped room full of students, postdocs, and computers, where our former undergraduate intern, whoops, let me sit back there again. Okay, our former undergraduate intern, Ivan Small, is presiding over the now growing search software. And then I mentioned the calm of space as the Hubble Space Telescope gradually does its part of the job. But of course, down on Earth, the same flurry of humans, Antti Fruchter and Nino Panagia, they make it possible to use this robot effectively. And then the last act begins with a view of the late night cleanup after the next celebratory party. But this time, there are entire cases of bottles of champagne left undrunk. We're lightweights. And they're all labeled with names of now scores of new supernovae to be analyzed. And so now, finally, a fresh relief team of scientists is now on the field at Berkeley. Rob Knopp, who thinks, types, and programs faster than I talk, and Peter Nugent, who juggles supernova theory and practice, Greg Oldring pulling together all the strains of the analysis and the search, and a final push of analysis has all of our undergraduate, Berkeley-based pre-graduate school interns working round the night and weekends. There's parallel computing at its finest, and first Julia Lee, and then Patricia Castro, Nelson Nunes, Robert Quimby, and all of these are now continuing careers in the field. And at last we fall gasping in a metaphorical heap with a surprising discovery about the universe that you've just heard about. And all this I'm describing, this is just on our side. This is what's going on our team. So I think it's pretty clear that all of this, the popular image of the lone scientist in the laboratory is just not our experience at all. For us, science is perhaps the most social activity that I can imagine. If you want to be with people, go into science, I've been saying. And this particular work was the product of this amazing community of scientists between the two teams. In fact, we represented a large fraction, not all of the community of scientists studying supernova, but a big fraction. And so I want just to finish by showing several more of the key players that I mentioned in this talk, representing some of the rest of that community. There's, we would all easily fit into this room, and it really was a product of our working together that got this. It wasn't just the three of us going off to our lone laboratories. So I think it's just important to have that sense of the social results. And then, of course, as a thank you in the Nobel lecture, I thought it was really important to point out that all of us were only able to do this at all because we had these amazingly supportive families who would put up with us during all these, this ridiculous time that we were spending at the telescopes during that period. And the staffs at the universities and the laboratories and the observatories were amazing. They would come in on weekends and all sorts of random times to help us when they didn't need to be doing that, and they helped us get through this period. So I want to point it out. And there was even some unusual action from the people who organized the funding. They really went out of their way and took risks on things that you ordinarily wouldn't see. And I've been encouraging that sense of risk-taking and funding, just giving people the freedom to get a little bit of work done. So I think that was all I wanted to tell you, except that the work isn't finished yet. And so I'm looking forward to seeing many of you, someday as our, joining us as our next tag team of scientists. And we'll hope to be working with you as we figure out what the answer is to this bizarre question that we're seeing. So let me stop there.
So thank you very much. Now, I've just got orders from higher up in university that it's important that we leave at the proper time. We are going to the castle for lunch with all the Nobel laureates that are here in Uppsala today. So maybe just one pressing question, if somebody has the guts to do it. Yes, please.
A good question. Right here.
So how does the Nobel Prize being awarded to just 3 individuals go along with the type of science that you do? What kind of description of science does it give? Does it go along with it?
I mean, it's obviously a very tricky problem for the sociology, and that's one of the reasons I was trying to convey this to everybody. Well, my understanding was that the Academy, the Royal Academy this year, they really made a point of saying in the citations labeling the names of the two groups. And I'm told that is a little bit unusual. That they were trying to capture something a little bit different in this particular award. And I will say that yesterday we had a symposium and then a dinner for the two groups, and I think it was just, I gathered that was also an unusual experience for a Nobel week, that we had 50 people here in Sweden, and they were all speaking yesterday at the science symposium at the Oscar Klein Institute in Stockholm, and they were all giving memories and stories at dinner, and giving Adam Bryan and I a good roasting of and I think that really did reflect much better that sense that that the committee really was trying to go for something a little bit unusual in this prize.
Okay. Now, I just want to say one final comment, and that is, you remember in Brian Schmidt's talk, he said that when he started this thing, this project, this was a big problem that he wanted to set his teeth in. And I think what this year's prize winners have done is to open up an even larger problem in terms of understanding, in physics terms, what causes this accelerated expansion. So that's something for you students, for a next generation of physicists and astronomers to take on as a big project to set your teeth into. And now I just want to end by again thanking Brian Schmidt and Saul Perlmutter, and give them just a little Christmas present. After all, it's Christmas soon, and this is just a little tiny thing which contains some cultural things to remember Uppsalavai. A practical notice for those that are joining for the lunch. We have to go immediately and take the cabs just outside the north entrance.